All right, so we are live on YouTube. So thank you everyone for coming for this webinar on condensed matter of the Brazilian Physical Society. Let me, as we usually do, let me share my screen, and I will, just one second, I will introduce first our next speaker. 2 weeks from now, we are going to have Professor Paulo Araújo from University of Alabama. On August 9th, he will talk about mechanical and thermal properties of carbon linear chains encapsulated by carbon nanotubes, a Raman spectroscopy approach. And today we have the privilege to have Professor Sankar Sarma from University of Maryland, USA, who will talk about searching for topological Majorana zero modes. Belita is a collaborator of Professor Sarma, and she kindly offered to introduce him. So Belita, you can start your introduction.
Hi, good afternoon, everyone. As Rodrigo said, it's a privilege to have Sankar Sarma give us a presentation. He's a theoretical solid-state physicist, and he's one of the most versatile and productive of all types. His background in physics started with a bachelor degree in Calcutta, and then he went to the United States in 1974 as a PhD student at Brown University, and he got his PhD in 1979. A year later, since 1980, he's a professor of the physics department of University of Maryland in College Park. Can you hear me?
Yes. Mm-hmm.
Now in Maryland, he holds the chair named by Richard Prank in physics in the department, and he was a distinguished university professor for a while, and he's a fellow of the JQI, Joint Quantum Institute, which is a collaboration partnership between University of Maryland and NIST. NIST is the Metrology Institute of the United States. In 2002, he created the Condensed Matter Theory Center, which I was there when it was created. And it was conceived by Sankar. And according to UMD president, he's the permanent director of the institute. And it's a very lively, very stimulating environment for visitors and students and professors. It's very dynamic and open to new ideas, and has high circulation of members between students, postdocs, and visiting. What impressed me more in Sankar is the amplitude of the subjects he treats and the variety of collaborators he has with all continents. Now, I could spend a long time talking about his qualities, but I'll just give you some numbers. And he has total of 95,000, over 95,000 citations, and the H index is 130. I don't know, because maybe last week it's already changed, and it changes every day, the numbers in his productivity. Then among his papers with more than 1,500 citations, the most cited paper is Reviews of Modern Physics in Spintronics in 2004. And he has contributions over 1,500 citations on topological quantum computation. We also reviews of modern physics, electronic transport in two-dimensional graphene, Majorana fermions, and the topological phase transition in semiconductor superconductor heterostructure. He's talking about subjects connected to this. And electronic screening and plasmons in two-dimensional graphene. Another one from 2010, a generic new platform for topological quantum computation using semiconductor heterostructures. Carrier transport in two-dimensional graphene layers. cell phone system theory of graphene transport, measurement of scattering rate and minimum conductivity in graphene, and a Nobel lecture in the origin, development, and future of spintronics. You see he has a lot of impact in condensed matter theory these days. And from the papers I mentioned, you can see the variety of subjects. He's really he's originating all these new subjects. So I let Sankar speak, and thank you very much for accepting the invitation.
Okay.
Thank you. I'll stop sharing my screen, Sankar, and you can share yours.
I'm going to do that right now. Yes. Oh, my screen should be up there.
Yes, we can see that.
Except it's the wrong page. I have to go to the first page. Yeah. All right. It's out there. Well, thank you very much, Belita, for that flattering and very, very long introduction. But I forgive you because you know me for a very long time and you're a very kind person. I think the most important thing is that I have had many, many, many collaborators. Belita is one of them. I have had several from papers with Rodrigo also. And I have collaborators from all the continents. Well, no one from the Antarctica, but all the other continents I have collaborators from. So more than 200 theorists have been my collaborators throughout my life. So that is, I think, the thing I'm most proud about. When you have a lot of good collaborators, well, some of your work will be good because you have chosen good collaborators. Okay. So what I want to talk about is a subject that's very topical, very active, and also I think very important and deep. And surprisingly, although it's deep fundamental physics, it has a potential huge technological angle, meaning today, all of good physics eventually goes into technology in some form, but this one may have technological impact more or less right away because it may lead to a quantum computer. So what it is searching for topological Majorana modes. Okay, so I'm going to explain topological, I'm going to explain Majorana, I'm going to explain zero modes, and I'm even going to explain searching. Okay, and then you'll see what the search is. So I'm showing you here on the right. Let me change my pointer to this. So on the right, I'm showing you one of the latest experimental papers. It's just a paper that came out, I think, last week, was posted last week. A new country and a new continent just came into Majorana experimental physics. So this paper came out of China, collaboration among a number of Chinese institutes, with Tsinghua University being the lead. And they are now claiming to have, they suddenly joined the search for Majorana through this, and they're claiming they have seen Majorana. And what I'm going to be talking about, and at this point, you will not understand what I'm saying unless you already know the subject, but this is the important thing. You see this red line here? This red line is a large conductance of the order of 2 square over h at 0 voltage. Normally at 0 voltage, you don't have current, right? But in a superconductor, you can have current at 0 voltage. And in fact, this current is exactly the mid gap, the bias of a superconductor. You see the superconducting gap here, superconducting gap here, and something in between, you have current at 0 voltage. And this is what everybody's searching for. This is what we predicted. And if this turns out to be this topological Majorana mode, and the word if is very, very important here, then this will be a very important physics discovery, fundamental physics discovery, and a very important topological. So you can see what is being plotted here in false color plot is the differential current, DIDV. The color large red means large values, 2 square over h. Blue or black means low values, okay? So this search actually began in 2018. This is a very similar experiment to that, equivalent to this. And what is being shown here, this is the first experiment. What is being shown here is some entity, I'm going to describe the entity in a second. It's actually a nanowire, semiconductor nanowire, which has become superconducting. and you are changing the voltage in this nanowire. And each of these lines corresponds to a different magnetic field applied along the nanowire. Okay. Usually good things do not happen in a superconductor when you apply a magnetic field. But here, notice what happens when magnetic field increases. At some magnetic field, the zero bias current peaks. This is the same peak you see here, okay? And this peak is supposed to be the Majorana. Well, we're going to hear the whole story. So this was the first experiment which created a very highly cited paper from Leo Cohnhaven's group at Delft. I think it was the Science Discovery of the Year in 2012 in Science magazine, this peak. Okay. And you can see it's a superconductor because overall the current is suppressed. This is the gap. Okay, this is the coherence peaks. The superconducting gap ends here. So this is a superconducting gap, roughly 400 MeV. So this is an experiment from Charlie Marcus's group in Copenhagen. Again, you see this is indium antimonide, this is indium arsenide, and this is also indium arsenide. Here the superconductor is niobium, here the superconductor is aluminum, here also the superconductor is aluminum. And again, you see very similar physics. This is very clean data. And you can see that a gap is closing as you increase magnetic field. And then at some point when the gap closes, something interesting happens. You get this zero bias peak. And this zero bias peak is supposed to be Majorana. Here is line plot for fixed magnetic field. When the magnetic field is zero, you're over here. You have nothing because it's a superconductor. You're looking in the gap. When the magnetic field increases, eventually you develop a zero bias peak. And this is very unusual. In a superconductor, good things should not happen when a magnetic field increases because it destroys the superconductivity. But here the theoretical prediction was that you should see the zero bias peak corresponding to Majorana. This is a very famous or very infamous paper from a Nature paper, which is now retracted. Again, very similar physics. The retraction will have no effect on what I'm talking about. Okay? Things I'm talking about are still valid. Again, gap collapses as magnetic field increases, and then a beautiful zero bias peak with roughly 2 square over h value. You can see how good the peak is here. This is the superconducting gap at zero field, beautiful gap. And then at finite field close to 1 Tesla, you have a beautiful peak, supposed to be Majorana. Okay, this peak goes slightly above 2 square over h. And then beta data was taken more recently corresponding with this experiment. This is an archive. You can see that this part, I'm enhancing this part. You can see the peak is actually slightly above 2 square over h, depending on various gate voltage or tunnel voltage that you use. Okay, this will become significant later on. And you can see better picture that the peak could be at 2 square over h, but generically it is not 2 square over h. It's either above or below. This is true in all these figures. Okay. And this is what we are looking for. Okay, this kind of peaks. And why is it important? It was important because in a paper in 2010, these are all famous physicists now. They're all tenured faculty members. Roman is a high-level manager in Microsoft. They were all postdocs at Maryland in this Condensed Matter Theory Center in 2010. Jaideep Sahu is at Maryland, Sumant is at Clemson, Roman is in Microsoft, and Tudor is in West Virginia. We made a prediction, and the prediction is this. This is a picture taken from that paper. Take a superconductor, aluminum, niobium, put a semiconductor nanowire on it, and we actually predicted which semiconductor you should use, indium antimonide or indium arsenide. Why those? Why not silicon or germanium? Because we need a nanowire which has strong spin-orbit coupling. Okay, we need a semiconductor strong spin-orbit coupling. So indium antimonide, indium arsenide are good candidates. And then what would happen? This superconductor would induce superconductivity in this nanowire because a superconductor is large, nanowire is small. So the nanowire will become superconducting due to proximity effect. And once it becomes superconducting, we said apply a magnetic field. And then this material will become a topological superconductor. Topological superconductors are a very interesting object. They will host Majorana zero modes at these ends, we said. And the way to see it is, what will happen is that as you apply this magnetic field, at first, the S-wave gap of the superconductor will go to zero. This is what you read in textbooks, that if you have a superconductor, you apply a magnetic field. It's called Clarkston limit. So when the spin splitting is equal to the Cooper pairing or the superconducting gap energy, superconducting pairing will be destroyed. SOF pairing will be destroyed. So the gap will go to 0. But what we predicted is, after that, if there is strong spin-orbit coupling here, a new gap will open. And this is the topological gap. This is not a simple SOF superconductor. This is effectively a spinless POF superconductor. And this gap size will depend on spin-orbit coupling. You see, this is for the large spin-orbit coupling, the gap is large. For small spin-orbit coupling, the gap is small. But there is always a gap. And this is a new kind of superconductor. This is a topological superconductor. And if you can achieve this topological superconductor, good things will happen. So we said the way to know is that over here, let's look at zero magnetic field. Zero magnetic field, you look at tunnel current, there's a black line, black dash line. Outside the gap, you have current. Inside the gap, you have nothing. This is what happens in a superconductor. Superconductor, inside the gap, nothing happens. So the current is 0 inside the gap. But what he said, as you increase magnetic field, and eventually you get to this side, so that happens roughly above 0.5 MeV. So when you go to above 0.5 MeV, so 0.25 MeV, nothing happens. The gap just shrinks. But 0.5 MeV, you will now develop a peak at zero bias. And this peak corresponds to this topological superconductivity. So you know whether you have a topological superconductor or not by seeing that you have developed a peak. Okay. And you can see this peak remains as you increase the magnetic field. The gap is going down, the peak may change in size, but the peak is always there. So this is the crucial point. Our prediction was very specific. Make this system, apply a magnetic field, do a tunneling spectroscopy measurement, tunnel current through this. If you see a peak after the gap closing, you have achieved a topological superconductor. And the first slide I showed you that experimentalists are, in fact, following our prescription and seeing this peak. This is exactly the same peak. This is exactly the same peak that we predicted should exist. So this is one of the few things in solid-state physics, condensed matter physics, where the phenomenon was predicted. The great discoveries in condensed matter physics are not prediction. There are some exceptions, of course. Superconductors are not predicted, right? Camarly-Gones saw it in 1911, and it took 50 years to explain it. And we also said that this peak actually will oscillate if you change the wire length. This oscillation comes from the fact that the two Majoranas will see each other. I'm not going to have much to say about it. Most of my talk will be on this part. Okay? So what is Majorana here? I told you about the search, okay, and topological. But what is Majorana? Well, I have to make a detour now. Majorana is the name of a person, Italian, Ettore Majorana. He was born in 1906 and he vanished in 1938. Most likely he fell from a boat. He was Sicilian. He was going from Napoli to Sicily. He's a very brilliant theoretical physicist. And he predicted something called Majorana fermions. He also did Majorana, the thing that's called Zener effect. Majorana actually had the first paper, but he didn't publish it. Enrico Fermi, who is not known for making exaggerated statement, said about Majorana that there are many categories of scientists, people of second and third rank who do their best but do not go very far. So that describes 99.9% of the physicists, I guess, at least by Fermi standards. There are also people of first class who make great discoveries, which are of capital importance for the development of science. And then he gave some examples of those, Galileo and Newton. And then he said, Majorana was one of those. So Fermi certainly thought very highly of Majorana. And in fact, this famous paper, Majorana fermion, Majorana did not like writing papers. Fermi actually wrote the paper for him. So Fermi acted as secretary for Majorana. So obviously he thought very highly of Majorana. Now, what I want to tell you is that this Majorana particle, Majorana fermion was really a subject of particle physics. So if you look at APS journals, very easy to do a search. I did, and I found that in the 20-year period, 1970-1999, there are 300 APS publications with the word Majorana in the title or the abstract. And essentially all of them are in particle physics or nuclear physics, all of them, which is where Majorana made his prediction. But if you go up to 1999, if you start from 2000, when topological superconductivity became a big subject, 2000 to 2020, in this 20-year period, there are 3,000 APS publications with the word Majorana in the title of the abstract. Okay, just title of the abstract, not in the body. 3,000, 10 times. Now more than 90% in condensed matter physics. Something happened. Okay, the subject switched from being mainly particle physics to almost entirely condensed matter physics, and the subject became much more popular, much more active. And what happened is what I just told you. People realized that in condensed matter physics, you can have something that is a bit like Majorana, but really has very little to do with Majorana talked about. So in some sense, the word Majorana here is a misnomer, but it's not a complete misnomer, and I want to explain to you what I mean by that. So Majorana fermions, which I'm going to describe in some more depth in a second, Majorana fermions are neutral fermions. Okay. They're fermions which are neutral. Most fermions you know are not neutral, right? Electrons, protons, they're not neutral, but Majorana fermions are neutral, which are self-adjoint. That's all you need. If you have a fermion which is self-adjoint, that means the particle is the antiparticle. So it must be neutral, but it must have something more also, okay? Neutrons are neutral, but neutrons and antineutrons, are not the same object, but neutrinos and antineutrino may be. If they're self-adjoint, with the same creation annihilation operator, they are Majorana. Now, for example, this particle physics is a really important question whether neutrino is a Majorana fermion or not. It's still an open question. This double beta decay, which experiments with large groups in deep mines are trying to see if neutrinos are or are not Majorana fermion. Right now, it looks like they may not be, but it's not settled. This is what Majorana had in mind. But Majorana and condensed matter physics are not Majorana fermion. They're not even fermions. They're non-abelian anyons. They are Majorana zero modes. Only thing in common is that Majorana zero modes, creation operator and annihilation operator are the same. So they're self-adjoint. So that's the only part that comes from Ettore Majorana. Other than that, it's totally different. These are not fermions. These are zero energy neutral defects. They obey non-abelian braiding statistics. They exist only in low dimensions. Okay, and they have been around only for 20 years, starting around 2000. This is why the subject took off. Originally, it was in fractional quantum Hall effect. Now, mostly in topological superconductor. So here is Majorana, as you look, and this is the Majorana we are talking about. Okay, these zero bias peak Majorana defects. So brief history of Majorana fermion to give a background. So Majorana asked this question, Ettore Majorana asked this question, Dirac equation has just arrived. And he asked the question, as you know, Dirac equation is complex, right? Are equations for spin-half particles necessarily complex? And obviously the answer is no. You can just do a very minor manipulation, take an imaginary part, add, and Dirac equation will become real. And then the answers are only real numbers. Okay, so then the particle is not complex anymore. And Majorana apparently did not like complex numbers. Some geniuses don't like complex numbers. This great Indian mathematician, Ramanujan, did not like complex numbers either. He did everything using real numbers. So the thing is, since it's electrically neutral, particle and antiparticle have to be the same. So gamma and gamma dagger are the same. So particle is own antiparticle. But it's a fermion, it's a Dirac fermion. It just happens to be a neutral Dirac fermion where the particle and antiparticles are the same. It's a solution of Dirac equation. It's just a solution of a real version of Dirac equation. So nothing topological about this Majorana fermion. This is just real Dirac fermion. For example, neutrinos may turn out to be Majorana fermion. If they do, you cannot do quantum computing with neutrinos. There is nothing topological about neutrinos. And they exist in all dimensions. They're three-dimensional objects. So Majorana's original work is relevant to particle physics. Okay. What we are talking about something totally different, except for the fact that this property is the same in both. So we are talking about emergent Majorana, which has this property. The possibility that the Majorana operator itself could be realized in low-dimensional condensed matter system. And it turns out if you do that, those objects are non-abelian anyons. You can do topological quantum computation with them. Okay? And they become topological objects. Question is, can it actually emerge in ordinary material? Okay. It turns out they can. This is what was understood in around 2000. So superconductors are actually natural hosts for Majorana. Now, as you know, superconductor is a ground state, has infinite number of Cooper pairs or indefinite number of Cooper pairs. So Cooper pairs are not the excitations of superconductors. Cooper pairs are, you can think of a superconductor, crudely speaking, as a Bose-Condensed set of Cooper pairs. What are the excitations? Excitations are called this Bogolub of quasiparticles. They are, the operator for them is an electron operator and a hole operator together. Okay, so these are so you can see that quasiparticle superconductors have Majorana character because they have both particle and antiparticle, electrons and holes. All you need now is U to be equal to V star. If U is equal to V star, then gamma is gamma dagger, right? So if you can make U is equal to V star, then the quasiparticles of that particular superconductor, where U happens to be V star, will obey Majorana property, Majorana operator. And how can this happen? That is basically saying particles and holes are the same. Particles and holes cannot be the same. It's because of the magic of superconductor, right? Superconductor Cooper pairs come for free. So you can convert an electron to a hole. That's called an Andreev process, because all you have to do is add a Cooper pair, right? Electron, hole, Cooper pair has 2 electrons, so it's the same. So the fact that Cooper pairs come for free because of spontaneous symmetry breaking is what allows you to have. Now, in normal superconductor, this cannot happen because normal superconductor, you have the index theorem that you are not allowed to have energies as 0, because what happens in normal superconductor, normal SF superconductor, for every positive energy state, you have an exact negative energy state. This is an exact symmetry for superconductors, particle-hole symmetry. So you have no 0 energy state. So you have a particle, you have a hole. So U is equal to V star is not allowed in normal superconductors. You cannot have 0 energy states. You cannot have mid-gap states in ordinary SF superconductor. Okay, because it's called Fermion doubling theorem. Okay, you need, because fermions come with spin, you need spinless superconductor. That means it cannot be S wave. You need spinless P wave. That's the minimum you need. So if you have a spinless P wave superconductor, then you can easily have this, and then you have a 0 energy state. That 0 energy state, by definition, is its own antiparticle, right? Because remember, each positive energy state is a particle. Corresponding, there is a negative energy state that's antiparticle. Well, 0, if you make it antiparticle, it's still 0, right? That means both particle and the antiparticle are now together at 0 energy. And this you can have if you have a spinless PUF superconductor. So the big question now, and then you create a 0 energy state. This is why experimenters are looking for this at 0 bias. 0 bias means 0 energy. In superconductors, 0 of energy has meaning. It's exact mid-gap. You learn in elementary school that energy 0 has no meaning. You can shift it, right? Not true inside a superconductor. Inside a superconductor, 0 energy has precise meaning because it's exact mid-gap. The precise symmetry prime, particle-hole symmetry. So question now is that do we have spinless PUF superconductor? It turns out in nature. So let me just go a little bit more. So this is a Bogolov-Degeneracy equation, basically BCS equation, solutions of this. So you have the particle-hole symmetry, basically says that this Bogolov-Degeneracy, which is BCS equation, if UV is a solution, then V star U star is also a solution. This is the exact symmetry I was talking about. Okay, and if this has energy, this has energy minus E. Well, if you have energy, if you have a solution with E is equal to 0, then it's particle-hole symmetry. It can neither be a particle nor a hole. It has to be neutral. Okay, for spinless fermions, this is guaranteed that you'll have a state at E is equal to 0, and that state, this excitation, this 0 energy excitation, which is neither an electron nor a hole, is our Majorana 0 mode. And why is it topological? So I'm going to, there are various ways of understanding it. I'm going to give you the simplest way of understanding. Let's say that you have this 0 energy solution because you're in a spinless PUF superconductor, you have it. And now you're closing the gap. Well, if you close the gap, this solution must go away because you don't have the topological system anymore. You have ordinary fermions. But this object is neither electron nor hole. How is it going to go away? In ordinary metal, you have either electrons or holes. You do not have an object which is both electron and hole. So you can now see when you try to make it go away and you bring the gap down to 0, this thing would not want to go away. Something has to happen for it to go away. And that's what it has to happen. Usually you come from this end, okay? That's called topological quantum phase transition. And if the system has a zero energy solution, you call it a topological superconductor. If it doesn't have it, then that's an ordinary superconductor. In this context, a trivial superconductor. Experimentally, by applying a magnetic field, you are going in this direction. Here, you do not have a zero energy solution because the system has spin and you cannot have a zero energy solution. Then over here, at some high magnetic field, you have a zero energy solution, that zero bias peak. In between, you must have a situation the gap vanishes, because when the gap vanishes, a continuum. And when you have continuum, you can have rearrangement. And that's what it's meant by topology. Topology, if you have this solution, it cannot just vanish. The gap must vanish first. So as long as you have a gap, this thing is protected. It's protected by the gap. This is the topological protection. Okay? And it turns out that if you have it, this thing cannot be either, this thing is not a fermion. So this thing is a non-abelian anion, Ising anion. What does that mean? You can easily see what it means. Two such, so this is one Majorana, this is another Majorana. Two of them together is basically like a particle or a hole, right? In ordinary life, you have only electrons or holes. You do not have Majorana. So that means anytime you create Majorana, you must create them in pairs. Okay. Two of them together is a particle or a hole. So if they're very close by, you have done nothing. You have just created a particle and a hole. But if you can separate them very far, then they have their own entity. They have their own existence. And then they don't know that another one exists. Another one is very far. Then this object is very strange. What is this object? This object in some sense is half an electron, half a hole. We don't have those things in real life. So it's an emergent object. This is no fundamental particle, half an electron, half a hole. But you have created it by separating them very far. Remember, if you put them on top of each other, this is just standard condensed matter physics, electron. But if they're very far, and in our system, they form at the end, two ends of the nanowire. So if the nanowire is long, they are separated. And when they're separated, it's a very strange object because two of them together create a fermion state, two states. So there is a degeneracy now. Having the two of them together or not having them at all has the same zero energy. And this degeneracy is a topological degeneracy, and you can exploit it. This is basically parity. As you know, parity is not well defined inside a superconductor. And this parity allows you to do topological quantum computation by braiding, and you will have a huge ground set degeneracy. If you have 2n of them in a system, you have many words, you have n words, you have 10,000 words, then you have 20,000 of these objects, and that will have a ground set degeneracy almost to the power 2,000. And this ground set degeneracy, this macroscopic ground set degeneracy, which is not coming from any symmetry. There is no symmetry in the problem. It's coming from topology. You can exploit it to do topological quantum computation because the degenerate subspace, and all you need for that's the qubit. This is the qubit. The fermion parity is 0 or 1. And you can braid them around each other, topological quantum computation. I did not have time to explain to you how it's done. It's very simple, actually, okay? But remember, they have to be very far. If they're close by, then they're not at zero energy anymore. There is energy splitting, and you cannot then do topological quantum computation because they're not zero energy. They're a little bit electron. So this is non-local parity because they're very far from each other. This is what Kitaev pointed out in 2001, okay? But if they're close by, what happens is that then they overlap, and you have a little bit symmetric, anti-symmetric state, like here is a Majorana, here is a Majorana. They overlap, and when they overlap, you have a little energy splitting, and this energy splitting actually oscillates, we showed. This is the part which you want, exponentially protection, topological. If they're very far, this splitting is exponentially small. This is the length of the wire. This is superconducting coherence length, very, very small, okay? But there is some oscillation, and you really want to be in a region where they're very far from each other, okay? If they're close by, you'll have this oscillation, and they will not be at zero energy. So that you have to keep in mind. Two Majoranas must be very far from each other. And if they are, I'm going to skip this, then you can take them around each other. I'm just going to show you the graphics. Here is a bunch of Majorana. You can take them around each other, and you can do topological quantum computation. Don't ask me how it works. It's if you do not know, my explaining you will take several hours. It's actually very simple, but it's quite technical. Okay. But this is all you have to do. Once you have created them, you just have to move them around. Okay. Once you have isolated Majorana, you just move them around each other, and you can do quantum computation. So here is a nanowire with two Majoranas far from each other. Here is another nanowire, two Majorana far from each other. And you can do topological quantum computation now by manipulating these four around each other. So we actually pointed out already a very long time ago in 2000 that a system like this will have zero bias peak. Okay, I mean, this is long before anybody talked about. And same year, actually, Kitai pointed out if you have these objects, he didn't talk about how to see them. We talked about how to see them. Kitai pointed out that if you have such objects, then there'll be this exponential protection. Okay, this exponential protection. This is the coherence length, and you can use them to do topological quantum computation. Okay, so this is why the subject took off after 2000. Okay, so that's why 2000 was a key year. It became a subject of quantum. And Kitai actually tried to propose a system that will have it. And he had the idea, maybe spin-orbit coupling would help, but he had the wrong conclusion that spin-orbit coupling does not help. And it took 10 years for us to understand that spin-orbit coupling actually helps. So he proposed in this paper, this is the first paper, that you can actually realize topological quantum computation in an ordinary material, just semiconductor. All you need is a superconductor, spin-orbit coupling, and spin splitting. So, spinless PUF superconductor does not exist in nature. If they do, you could have just used them. But spinless, as far as we know, spinless low-dimensional superconductor does not exist in nature. But you can create it. All you need is three ingredients which are common in condensed matter physics. You need a proximate. You need a superconducting gap, you need a spin splitting, and you need spin-orbit coupling. Three of these things together, you break time reversal invariance and break spin rotation explicitly, that converts an ordinary S-wave superconductivity to spinless PUF superconductivity. And this paper we explicitly showed that. So you do not need a spinless PUF superconductor in nature. You can combine semiconductor, which is spin-orbit coupling, superconductor, which has SF superconductivity, and a magnet or a magnetic field to create this non-local parity. So the new idea that we had, this paper became very famous. Belit actually mentioned this paper. The new idea here is that spin-orbit coupling plus Zeeman exchange of Zeeman spin splitting can convert ordinary SF superconductivity into topological pure superconductivity at high enough spin splitting. Now you see why you need to apply a magnetic field and why the magnetic field has to be larger than some amount. This is chemical potential. This is the superconducting gap. Okay, you basically will create a new kind of superconductor when the magnetic field satisfies this inequality. And quickly, we and another group realized that this is even better for a nanowire because you can apply the magnetic field along the wire. Take a nanowire with strong spin-orbit coupling, put it on a superconductor, apply a magnetic field. There'll be one Majorana here, one Majorana there. Basically, what is happening is you are creating a gap, this gap, and if you put the superconducting gap right here, then there is a spin texture at the Fermi surface, and that spin texture creates just the right kind of spinless superconductivity, spinless PF superconductivity you need. So you can induce spinless PF superconductor. You can engineer it. You don't need to have it naturally, okay? So we worked out the whole theory analytically and showed that there should be spinless PF superconductivity in this system provided this condition is satisfied. This is the Zeeman splitting. Spin splitting should be larger than this quantity. This is chemical potential, which you can control by gate voltage. This is superconducting gap, which you control by having a actual superconductor. And we did numerical work showing that indeed, this is a superconductor, this is a topological regime. As you are increasing magnetic field, is the chemical potential. As you increase the magnetic field, when the magnetic field passes this limit, you have a topological regime. This is where the PUF superconductor is. This is the SF superconductor, and this is the point of that topological quantum phase condition, TQPT. And the simple picture is what I just told you. So interplay of spin-orbit coupling, Zeeman spin splitting, converts an ordinary superconductor into a spinless PUF superconductor by lifting this fermion doubling constraint. And we then made this prediction that I already talked about, okay? You can numerically calculate. This is Theodore Stanescu's work from early on. This is not schematic, this is actual calculation. He found just numerically solving BCS equation. that for spin splitting larger than this number, in the gap, this is the gap, above the gap, you have all these fermionic states, but in the gap only state, you have a 2 zero energy state at the two ends of the nanowire, you see? And as long as there is no overlap, these are Majorana. This is one, this is one, this is an emergent state. But when you go below the gap, they vanish. You just have a gap. And in between, precisely when this thing is equal to that, the gap closes. Okay, when this thing is equal to that, the gap closes. This is just direct numerical work. So Majorana modes should emerge at high magnetic field. And right after prediction, Leo Cohnhaven's group saw, they, look at it, the experimental system is exactly like a theoretical proposal. Here is the nanowire, semiconductor nanowire. Instead of putting the superconductor below it, they put the superconductor on the top. This orange or red is the superconductor, niobium. So there is a proximity in the superconductivity. And this is the tunneling contact. This is gold. So you're measuring current, tunnel. And then there are all kind of gates here to change the potential. So you're changing the potential, bias voltage, to see current, tunnel through the tunnel. This is a tunneling current. And there is a magnetic field here along the wire. So magnetic field is changing. Here is theory. At low magnetic field, there is nothing, just gap. At high magnetic field, there is zero bias field. Here, low magnetic field, there is nothing. At high magnetic field, there is something. So obviously, this created tremendous sensation. Only question is, yeah, it looks like what the theory is saying, but now there's a very big claim, right? That you have created topological Majorana mode. It's a very, very big claim. So you have to now validate it, that what was predicted is what is being seen. So many experiments were done right after the original experiment from Delft, verifying this. You can see this is the original Delft measurement. Here is a measurement from Weizmann Institute. You can see all of them have the same features. Details may vary, but all of them, when you apply magnetic field, eventually see a zero bias peak. This is, I think, Charlie Marcus' original data when he was still at Harvard. This is, I think, from Urbana. These are all experiments for different groups, showing the main thing you should look at: low field, there is nothing; high field, there is a peak. Now, you notice that these superconductors are very bad. Look at how soft the gap is. The gap doesn't look like hard gap at all. Very soft gap. A lot of harmonic states in the gap. Okay? Why? So we pointed out in 2013 that this is because of disorder. The superconductor semiconductor interface. This interface experimentally is very poor quality. You can see that it's very poor quality because they're creating it in this manner. So there's a lot of disorder at this interface. So it showed in 2013 that because of this lot of disorder in the interface, the gap becomes soft. So we said in this reserve letter in 2013, our work indicates that improving the quality of the superconductor semiconductor interface so that the proximity tunneling amplitude is uniform along the semiconductor nanowire would go a long way in enhancing the gap in the hybrid structures being used for studying Majorana mode. And right after prediction, Charlie Marcus's group actually did that. This is the very important experiment. Instead of doing the interface just by putting some superconductor, they created an epitaxial semiconductor superconductor interface, indium arsenide and aluminum. And look what happened immediately. The gap became hard. This is what the gap looked like before. And this is what this is the experiment. And this is theory. So the gap became hard and experiment and theory agreed. So now everybody uses this epitaxial system. So the zero field gap is very hard. So this is a huge improvement where theory contributed very substantially. It's mainly an experimental achievement, but theory suggested what needs to be done. Now the most important question, is this really Majorana or is this something else? Well, last 20 minutes, I'm going to tell you the subject has become very complicated. I'm personally convinced that although huge progress has been made, and I believe we are going to see Majorana one of these days, I also believe Majorana modes have not been seen. These zero bias peaks are something else. So there are many papers on it, but I'm going to show most of the results from this paper with my student Hai-Ning Pan, which introduced the terminology good, bad, and ugly into this literature. So experiments so far only probe zero bias conductance in NS tolerant spectroscopy, right? Just as theory predicted. And they have a superconductor and they do tunneling spectroscopy measurement. So the two papers I'll talk about is this paper from Copenhagen, Nichel et al., and the paper Zhang et al. It's corrected version. This original paper is retracted, but for our purpose, it's all the same. So this is experiment. This is the experiment from Copenhagen, Charlie Marcus's group. Beautiful data, right? This is magnetic field increasing. You can see gap closing and beautiful zero bias peak. This is what is thought to be Majorana. Here is data from DELT. This is indium antimonide and niobium. This is indium arsenide and aluminum. This is indium antimonide and niobium. Again, the same physics. The gap closes and you have beautiful zero bias peak. It looks like exactly what we predicted. And here is theoretical simulation by Heining Pan. Okay, you can see it looks just like experiment, right? You do agree it looks just like experiment. Unfortunately, theoretically, we know what we are doing, right? Theory has a huge advantage over experiment. Theoretically, we know everything. Experimental, you do not know what it is. You just see something. These are not Majorana. These are all created by disorder. This peak that you see is not Majorana. This is disorder-induced zero bias peak. Look how well it agrees the experiment. Okay, so we call these ugly peaks because these peaks are caused by disorder. Everything is exactly the way I said it is, but now you're including disorder and non-perturbativity in the theory. You have to include non-perturbativity. Also, disorder is just random disorder here. Similar peaks could arise from a inhomogeneous potential, some smooth potential varying in a deterministic manner, as would happen if you have gates. That also produces peaks just like that. Again, these are not Majorana. These are peaks created by inhomogeneous potential. Now, of course, if you have real Majorana, no disorder, that also has zero bias peak. But then you should see oscillations. Why should you see oscillations? You should see oscillations because these Majoranas are not that far. These wires that they're using are rather short, actually, okay, experimentally. I did not emphasize that, but the experimental wires, the length here is the order of a micron or less. And superconducting coherence length is probably larger than a micron, okay? So the Majoranas actually see each other. This is our simulation. And remember, I told you when the Majoranas see each other, they have splitting, and you can see the splitting here. You see those oscillations, oscillatory structure. That oscillatory structure is coming from Majorana oscillation. Experiment doesn't see any oscillatory structure. So you see this is what is going on. In fact, I'm convinced this is what is going on, okay, right now. But that doesn't mean that we cannot go there. We just have to know what is going on. We have to remove disorder. It's just a question of careful experimentation and spending more money in improving material science. So this is, the huge theory. I'm not going to bore you with all the details of the theory. You should read the papers. We did basically what you do. We solve the same Bogolov-Dejean equation that I showed you before. Here is the Bogolov-Dejean equation. This is the Nambu tau z. This is the superconducting part. This is the spin splitting part, and this is the spin orbit part. This is the spin splitting part, and this is the superconducting part. This is the pristine theory that's I was showing you. Now we add either a deterministic potential or a random potential and solve the same problem. Okay, non-partially. We just diagonalize the whole problem exactly. And we sometimes include a self-energy effect also. Okay, so good Majorana is when you just have this pristine theory, okay, without any disorder. Bad Majorana is when you had an inhomogeneous potential in addition to the pristine situation. And ugly is when you have strong disorder. In general, of course, you'll have both. Whichever is stronger will win. So we distinguish three kinds of zero bias peaks you can have. Good zero bias peak, which is the original thing we talked about and everybody thought experiments saw. This is what would lead to topological quantum computation. Bad, which comes from inhomogeneous potential, some potential smoothly varying along the wire, maybe because you have a tunnel gate or something. And ugly is just uncontrolled disorder that the semiconductor may have because of material is not perfect. Well, this is the good with some disorder. Remember, since it's topological, it has some protection. A little disorder doesn't destroy it. Some disorder, changes things. So I'm showing you what are the two figures. I'm showing you now the zero bias from left and the right. Remember, since it's topological, you should see same physics from both ends if it's really topological. So if it's good, even if you have some disorder, it shows very similar structure from two ends. Because of disorder, it's not perfect. And these are for different situations. It's, so you're adding different amount of disorder, but all small disorder. Amount of disorder, it's smaller than chemical potential. And there is some, various funky things are happening, like disorder is creating a non-drape state, but you still have the good Majorana because disorder is not very large. Well, now the disorder is very large. When disorder is very large, you get beautiful structure, beautiful zero bias peak. In fact, in some sense, these peaks are even better than these peaks, okay? But unfortunately, these are disorder in the zero bias peak, class D peaks. And now look at left versus right. They look very different because disorder is not topological. There is no reason for left and right to show similar physics. And you can see here, the zero bias peak is on the left, there is nothing on the right. Here, the zero bias peak is on the right, nothing on the left. Here, the zero bias peak is on the left, nothing on the right. So there is no correlation. That means it's trivial, not topological. Okay? You don't have two topological objects at two ends, as you must. Remember, I told you, Majoranas must appear in pairs. One Majorana cannot happen in nature because you don't have a half electron. So here you have Majorana, but you have a pair, both ends. Here you do not have Majorana. Majorana's on top of each other. Okay, ugly. And we call this, this is good with some other superconducting gap disorder. Again, if the disorder is small, you have good Majorana. Both ends, you see nice peak. And this is ugly with strong disorder. Again, now disorder in G factor or something. Again, you have peaks only from one end. Okay. So what did we learn? We learned 5 years after the experiment that you have strong disorder that could give rise to peaks on its own. And those peaks sometimes should look much more beautiful experimentally than the good Majorana peaks. Okay. So good, protected against small disorder. Small disorder is protected because topological, but the disorder is very strong. Of course, it's not going to be protected. Then you could have new kind of peaks, ugly, which would not have end-to-end correlation. In some cases, you may have accidental end-to-end correlation because the disorder somehow turned out to be very similar. But that'll be very accidental. That's not generic. Here is generic, and you'll have no Majorana oscillation. You see, there are no oscillations here because there is no Majorana. So why should there be oscillations? Okay. So there'll be two differences. Here, you'll see very similar peaks from both ends because it's topological, and you're going to see Majorana oscillations. Here, you may see beautiful peak, but only from one end, and you're not going to see any Majorana oscillations. And you saw experimental data see no sign of any oscillations. Okay. So this is, again, we actually wrote this paper. This is the Copenhagen sample. Our simulation reproduces it almost quantitatively. This is a Delft sample. Our simulation reproduces it almost quantitatively. By the way, you wrote our paper before all this retraction business happened. So I never took any of this seriously. I never took the seeing twist coverage. I wrote papers like this is all disorder. Okay. So the retraction has nothing to do with the physics that I'm interested in. I already knew that those things are not Majorana. Okay. So coming back now, so our paper was long before the retraction shown. In fact, I gave a talk in APS March in 2018 where I pointed this out, that these things are not Majorana, they're coming from disorder. Okay, so our ugly simulations with just disorder, in the BCS equation, produce trivial zero bias peaks in excellent agreement. You can go look at the paper, the agreement, okay, with the best available nanowire results. These are the best available nanowire results, and we get exact agreement, okay. And what happens is that both in theory and experiment, there's a lot of fine tuning. Experimentally, they look at 80 samples and they see some signal in one, and then they fine tune it by changing all the gate voltages. Obviously, they have to fine tune it because this is disorder induced. It's not generic. So we fine tune it also. And the amount of fine tuning in the two are about the same order. We also see it roughly 2% of the cases, okay? 2% of our zero bias peaks are this beautiful. Experimental is more like 1%, okay? So experiment probably has more disorder than even our theoretical sample. These things you really have to know that experimentalists are doing it, those things, okay? You would not know that by reading Nature and Science, that, it's not generic what they're seeing, okay? It's the moonshot approach, you send it, if it lands on the moon, you have success, okay? So we then did more work, theoretical work, showing that, this is experiment and this is theory, and they look very similar. Okay, I mean, I'm telling you, they really look very similar. Okay, And I then was convinced that this famous paper, Quantized Majorana Conductance, saw disorder-induced peak, not Majorana peak. Okay, the 2 square over h is just accidental there. So let me show you what is going on. Later on, the Delft group found that their lock-in had a calibration error. So what they thought was 2 square over h is actually not 2 square over h, it's 10% more. Well, there is no Majorana quantization at 2.2 square over h. So if you see 2.2 square over h, it definitely is not Majorana. And that's exactly what our theory says also. Our theory says that the peak is around 2 square over h, but it's not exactly 2 square over h, okay? So I'm going to show you in the next page. So this is experiment. This is experiment. And as you can see, if you look crudely, it looks like it's 2. This is the original nature. And then now better data with everything corrected shows it's really not exactly at 2, slightly separate, slightly away from 2. And it's not really completely stable. And this is our simulation. You can see our simulation is also it's pure disorder, okay? This is disorder-induced peak, and you can see it's not exactly at 2. Accidentally, it could be at 2 in one particular case because you're changing all the wedge voltage. You can always fine-tune and make it 2. But the moment you change the voltage, it will deviate from 2. If it is real Majorana, it will never deviate. It will remain at 2. So you can see that our theory reproduces the experiment. But our theory, these are ugly peaks. These are disorder-induced peaks, okay? So quantization is not equivalent to Majorana. You can get quantization accidentally because you have fine-tuned everything to be just at this point. When you change things, it will go away. So just observing, so if somebody tells you, I have quantized Majorana conductance, you can safely tell him that Sankar Sarma told you, that does not mean you have seen Majorana. It goes one way. If it's Majorana, it will be quantized. But if it's quantized, it will not be Majorana, okay? You know, every bearded object is not Karl Marx, right? Just because Karl Marx had a beard. Okay, so point is that we have to be very, very careful here. So one specific and concrete conclusion of our extensive theoretical work on Majorana nanowires is that what most experiments, I would say all experiments have reported to date. The Beijing paper came out just last week. I'm saying in most likelihood because one can never say with 100% certainty. If you're a scientist, you know nothing is 100% certain. But I'm as sure as I can be that these are all ugly peaks created by disorder. Okay, let me see how I'm doing with time. I mean, I'm basically okay. Yeah, I'll be done in 5-6 minutes. Okay, so this is what you have to keep in mind. That is all disorder. Okay, disorder produces very nice zero bias peak. Here is a direct comparison in a short wire between disorder zero bias peak and Majorana. See, Majorana there is almost no peak, but here you find a peak because the wire is short. Majorana are split here. So recently with the Delft theory group, with a very large scale, the kind of things that Rodrigo and Belita like, first principles, you know, we did a full self-consistent LDA calculation. We took the 3-dimensional actual structure, superconductor, semiconductor, okay? And we used a huge computer to solve the LDA problem precisely, to including the superconductor. So it's a demanding calculation. But one electron calculation. So superconductor, semiconductor together, we calculated the electronic structure instead of making a simple 1D model. And then we did the tunneling conductance calculation. And you know, you should look at the paper. And the main conclusion here is that if you're getting a peak, which is slightly above 2 square over h, this is guaranteed to be disorder. It's not even inhomogeneous potential. Anytime we have some disorder, we find peak that could be larger than 2 square over h or smaller than 2 square over h. So, you know, so conclusion of this is that very realistic calculations verify what I just told you. Okay, this paper just came out that if your conductance is above 2 square over h, you can put in the bank that it's not Majorana. Okay, it's disorder. And as I told you, these experiments mostly see a peak above 2 square over h. You know, so you need very stable, if you have very stable quantization, like here, that's being produced by inhomogeneous potential. So you cannot win either. So this is what we call bad, and this is what we call ugly. Bad gives you stable 2 square over h, ugly gives you slightly above 2 square over h. Okay. So zero bias peak quantized is necessary but not sufficient. Okay, this is the message, which is something, somebody has a question, it looks like. Somebody has but I'm almost done, so maybe we should hold the question. So very recent work, we included a very realistic calculation, like this kind of calculation, even more realistic now, charge impurities. Can you do disorder calculation with? So we put charge impurities and this self-consistent calculation, okay? This is like Belita and Rodriguez field, As you two know, I avoid doing this calculation, but Tudor loves this. So we teamed up with Tudor, did these calculations. These are very difficult calculations on very large computer. You have superconductor, you have semiconductor, you have disorder, you have self-consistency. But the bottom line, you should look at the papers. The disorder could be very large. Basically, the reason we did it is to see, can you put a limit on what the disorder should be for you to be able to see good Majorana? Okay. And so we did a lot of calculations. I'm going to go to the punchline. Okay. This is that phase diagram with and without disorder. Let me not get into the details. You should read the paper. This is the pure phase diagram calculated in two different ways, using two different criteria. You see beautiful, pristine phase diagram. This is numerically calculated phase diagram, LDA calculated phase diagram, LDA including superconductor. This is what happens when you have disorder, moderate disorder. You get a lot of peak outside. These are the trivial peaks. Okay. If you make the disorder stronger, you get a lot of things outside and things disappear from inside. If you make it still stronger, things almost completely disappear from inside. Everything is outside. These are all trivial peak, almost nothing left inside. We can keep on increasing disorder. Okay. This is Heining-Pan's unpublished results. Very strong disorder, you have nothing. You just have these peaks. Okay. Look at it. All these are zero bias peaks. Okay. But it's like completely coming from random disorder. Very dark red are 40 square over H. And if you look very hard here, you'll find something exactly at 2 square over H at some point. Okay. Which is what the experimentalists are finding, okay? You can see it's roughly, you see this little white line? If you take the area of that white line and calculate, it's roughly 1% of the area, okay? And this is what I was telling you, that if you keep on looking, you'll always find something which is at this value. This is very strong disorder. There is no topology left at all, but zero bias peaks still show up. These are disorder in the zero bias peak, okay? And I am afraid that this is the situation we are in, okay? As I said, scary realistic phase diagram. It's so scary, I have not published it yet. But we are writing a paper, huge long paper, pointing out all these problems, okay? But the great thing, so basically large zero bias peak fine-tune. By fine-tune, I mean you can find a twist cover. If you tune very finely, if you use a tooth comb to look through it, you're going to find them. Here is one, but they don't mean anything, okay? So you'll find large zero bias peak. You'll find them from both ends at different places. You saw this is very bad. So this is, let me just skip this. This is really the same kind of calculations done more rigorously, okay? Tudor Stanescu did this, okay? Very rigorously, okay? So let me just go to the bottom line now. You can see when for strong disorder, so for weak disorder, he finds beautiful phase diagram. As disorder increases, it becomes less and less beautiful. And then for strong disorder, there is nothing, okay? Just zero bias peaks everywhere, which have no meaning. Well, so what is needed? Most important message is, just because you saw 2 square over H doesn't mean you saw Majorana. It goes in this direction. Majorana implies quantization. Quantization does not imply Majorana. Okay. All right. So what do you have to do? It may sound like I'm giving you a very depressing picture. It's not depressing at all. We have diagnosed the problem. If you do not diagnose the disease, you're not going to be able to solve it. Of course, sometimes you diagnose the disease, still cannot solve it, but let's hope it's not like that. So what do you need to do? Well, MGMs have not been seen yet, I told you, but all the ingredients are there. The system is behaving the correct way. Theory and experiment agree, we understand the system. Understand a very complicated system, 3 layers, magnetic field, semiconductor, superconductor. We understand the whole system. We understand it. They will be seen. Because all the features that the experiments are seeing, I can explain. I showed you, I spent an hour showing you that. I can explain from very simple model theory all the way to very complicated simulation theory. Well, we have diagnosed the problem. You have to reduce disorder. And those calculations show how low the disorder has to be. For these materials, indium antimonide, indium arsenide, the level of charge impurity density should be below 10 to the 15 per cubic centimeter. This is the critical physics. So you know what needs to be done. So this is not a matter of money also. Make the material purer and purer. This can be done. In gallium arsenide, a fractional quantum Hall is studied. This number is 10 to the 13. Now, indium antimony and indium arsenide, people have not put in the effort. You have to put in the effort. Nobody said finding Majorana is going to be easy. It's going to be difficult. And right now, the disorder is probably factor of 100 to factor of 1,000 higher. This number is probably 10 to the power 18. Certainly 10 to the power 17. I think it's more like 10 to the power 18. So reduce the gap, reduce the disorder, try to increase the gap, use longer wear, do non-local measurements. You will see everything. Okay. No single experiment will suffice, but this is the most important thing. Once you achieve this, I'm pretty sure beautiful zero bias peaks, quantized, will appear from both ends, and then you can break them, and you will have Majorana. And with that optimistic note, I'll stop. Thank you.
We thank you, Sankar. Thank you for this very illuminating talk. As we usually do, people can ask questions here at the Zoom, or I can also I will be collecting questions from the YouTube chat as well. So,
I'm very happy to answer questions. I have time.
There are already two questions. The first one is from Belita. Belita, you can go ahead and ask your question.
Can you hear me?
Yeah, I can hear you clearly.
Okay, so I have two general questions. First one is, I remember you did not believe quantum computing would happen in this century or something. Now, you are looking still for a new platform, and Majorana Fermi's topological way of doing qubits. But given the most recent developments in Google, do you still think it's impossible to have a quantum?
Yeah, let's be nuanced here. I would never make a statement, it will never happen. That's too strong a statement.
Not too soon. I said it's not coming soon. I think it's
going to be very, very difficult. First, the question is, quantum computing is an ill-defined term. What is meant by quantum computing? If you are talking about factorizing, I don't know, 15, 3 times 5, and you factorize 15 and using quantum, that's a quantum computer. Okay, so what you see, this gets into like rhetoric and people attack each other.
No.
What I'm talking about is a commercial quantum computer which can factorize numbers classical computers cannot do. That's going to be very, very difficult any way you look at it. But we have made enormous progress, and right now we should look at it as a topic in research, because we do not know.
Yeah, but now the times will not be as long as we expected.
Right. Now, I still do not know whether a quantum computer, in the sense that a computer that can factorize numbers that classical computers cannot, will happen. I do know it's not going to happen in the next 10 years. It may not even happen next 20 years, but I'm not willing to say it will never happen, because that's a dumb statement, right? Newton did not know that his laws one day would lead to Boeing 747 planes, right? So the thing is that I'm not willing to say it will never happen. I can only talk about next few years. It's unlikely to happen in next few years because the problems are very challenging. You are correct that there has been spectacular progress in regular circuit level quantum computing. But where has the progress been? Nobody has logical qubits. Progress has been using physical qubits. You can do many interesting experiments. And I think that's fantastic from a fundamental physics viewpoint. We are learning a lot. We are making progress. But that is not necessarily progress. I mean, that's progress, but very little progress towards logical qubits. So that has nothing to do with my talk. So coming back, I'm going to answer your question indirectly. Okay. Suppose in 1930, you had the idea that you can make a cell phone with transistors, okay?
Okay.
With not transistors, with 3-terminal devices, okay?
Mm-hmm.
And 3-terminal devices existed in 1930. They're called vacuum tubes, okay? Radio already existed. You'd say, I can never make something like this, even if you are, you could see far into the future, because the size of that will be larger than the size of the Earth, because you need to put 1 billion transistors, 1 billion vacuum tubes. 1 billion vacuum tubes will, be larger than Brazil. So you will conclude you cannot make it. That conclusion have been wrong because a disruptive technology came in, transistors. It was developed over a 50-year period, and then we found out we can actually put 10 billion vacuum tubes into, a 1 centimeter by 1 centimeter device. There was no way to say it in 1930. This is not because of any fundamental breakthrough, right? It's pure technology. It's not something you want to figure out by thinking, okay? So when I say the topological, so my view is that when I look at all the problems circuit level quantum computer has, how many problems you'll have to solve, I feel dizzy. I feel like that's like trying to create an iPhone with vacuum tubes, okay? Because all the things that you have to solve. We need something that transistor of quantum computing, and topological quantum computer may be that. But that doesn't mean it's going to happen. There is no logical reason why transistors happen. As you know, original transistor was a point contact transistor, and it was in germanium. That did not go anywhere. So what I'm trying to say is that you need to distinguish what I'm saying. Topological quantum computer, if it happens, it solves many of the problems of regular quantum computer in one stroke, okay? But that does not mean it's going to happen. So I'm still optimistic, but it's a huge challenge.
Oh, okay. But I feel you are more optimistic now.
Thank
I
you,
am more optimistic because a huge amount of resources are being put into it, huge. And the challenges are technological. This will not be solved in universities. You need much larger context, okay? And those larger contexts exist now, as you know. I don't want to name the companies, but you named one of them. The fact that very large companies and very large countries are interested in developing it is a very good sign. That's what would be needed. It is more like creating LHC and seeing Higgs than like working in University of Maryland lab and publishing in Nature or Science, okay?
Okay. Well,
Thank
maybe I
you,
have
Melita.
more
Thank you.
that more people talk.
Yeah, let me take a question from the chat here. There's a question from Gabriel Schroeder. Congratulations, very exciting presentation. How important is the spatial localization of disorder for these effects at semiconductor or interface? I think perhaps he meant the spatial distribution.
Spatial distribution.
Yeah.
It's a very good question. It's very, very important. What they are, obviously, and we are writing a paper which is becoming a 50-page paper discussing these issues. Right now the disorder is so huge that those things don't matter. Right now the disorder is everywhere. It's in the bulk, it's in the surface, it's the interface, everywhere, okay? I'm telling you the truth. Right now I believe that the amount of disorder is 1,000 to 10,000 times more than what is necessary, okay? You need to have no more than 10 impurities per micron. So in one dimension 10, right now the number is more like 500 impurities per micron, okay? So now 50 cube is a very large number, okay? But these are charge impurities, and you really do not want them to be at the surface. If they're in the surface, it's very deadly, okay? But these are good. You ask a very good research questions, and we are working on it, okay? Because we want to tell the growers how they have to improve their sample. But zeroth order, they have to reduce the number of impurities. The problem is, which is implied in your question, in semiconductor, the impurities are infinitely charged impurities. In fact, they're mostly sodium ion coming from people's sweat, because even in the ultra high vacuum environment, there is some sodium ions. Sodium ions are very mobile, and these are charged impurities, and charged impurities have very strong effect. But these are questions that we can answer theoretically, and we are working very hard. And we are answering them using our whole three-dimensional bulk program. And the companies which are working on it actually are doing it even more thoroughly than we are doing. They're not publishing it, it's proprietary. But it's a problem we are all very aware of. It's a very good question.
Thank you. Thank you, Gabriel. There's a question from José Royos. José?
Hi. Thanks for this exciting talk. My question is also about disorder, since you talk too much about it and saying disorder does lots of things. Could you tell us what is exactly the phase that is being replaced, the topological phase is what now? Is
I'll tell you precisely. I avoided that. This is, you know,
also could
so
you tell us about the transition itself? How
Correct.
the universality class change?
Very good question. So let me just answer it directly. Without interaction, suppose you ignore electron-electron interaction, it's a one particle problem. So we can just use the periodic, the classification scheme, the so-called tenfold way to tell you what it is. So the state is a 1D system. In the strict 1D limit, there are just two phases: topological superconductor and Anderson insulator. There is nothing else. Okay. So what happens, Majorana? So topological superconductor, we know what it is the wire with two Majoranas and two ends only, right? That's the topological superconductor. I'm talking about the critical phases. The other phase is the strong disorder phase. So RG flow is to strong disorder or zero disorder, okay? In between is all crossover. So for strong disorder, it's an Anderson insulator. You have infinite number of Majoranas localized along the wire, okay? These are the only two phases, okay? And I alluded to the word class D in some of my papers, and that's what I'm alluding to. The strong disorder phase is basically a phase where you have infinite number of Majoranas. Easiest way of thinking about it, there's a very physical way of thinking about it. Since you asked me, I'll answer that. Imagine you have the 1D wire, and you have a bunch of impurities in there. You can think of this as many, many wires, right? Each impurity divides the wire into two ends, okay? Cuts the wire into two ends. Each of those ends now would have Majorana, okay? So impurities, if you have like n impurities, somehow they are creating 2n Majoranas, okay? And if those Majoranas are close by, you'll have overlap and you're not going to have topological superconductor. So physically, that's what is going on, okay? So that's why how many impurities have per micron matters, okay? So yeah, so the answer to your question is, of course, you're in a crossover regime, but the strict, from quantum phase transition viewpoint, the strict phases are Anderson insulator or topological superconductor. Okay, and experiments are much closer to the Anderson insulator phase now than the topological superconductor phase, okay? In high magnetic field, it's a class D system.
Thank you.
Thank you, Jose. There's a question here from the chat from Lucas Schilanti. Thank you very much for the great talk, Professor. Does it make a difference on the transition from trivial to topological superconductor if, for instance, the exact magnetic field needed for the transition is applied and only then the temperature is decreased to reach the critical one of the nanowire?
No, unfortunately, those things will not make any difference. I understand what you're asking. You're saying that suppose I do all my orientation when the superconductor is still metallic and then reduce. No, that would not help. But experimentally, there is a bigger problem, which you don't have in theory. Experimentally, you do not know what the topological quantum phase transition point is, right? Because experimentally, you do not know the chemical potential. This is the biggest problem. You know, this nanowire, experimentalists have no control over it at all. They do not know the carrier density in there. We know because we saw the self-consistent problem, but they know nothing about it, okay? And there is some intrinsic doping, you know, Rodrigo and Belita know that when you put an empty semiconductor in a superconductor, semiconductor will not remain empty, right? There will be some carriers coming in to make the work function the same. And experimentally, they don't know anything about the Schottky barrier, Fermi surface spinning, all those things. And all those details, which cannot be settled theoretically at all, have to be carefully worked out. And remember, you know, we take existence of chips granted today. We expect chips to become faster and faster, 10 billion transistors, but it was like incredible effort by thousands of engineers over a 56-year period that made this happen. Why should we expect topological quantum computer, which is, you know, much, much more sophisticated, happen just because some experimentalists in some labs, in some universities, just put some nanowire on superconductor? So my worry is that, not my worry, what I would hope, you know, that my papers and my talks will convince people that this problem has to be taken very seriously. This is nothing short of like trying to create a Pentium chip, okay? And you are not going to do that with two graduate students in a lab. So answer to your question is that no easy trick will solve this problem. You have to first purify your material and then do experiments.
Okay. Sorry, there was a follow-up question from Lucas related to this one. So he further asked, also, could you comment on a little bit more on the importance of the spin-orbit coupling in this scenario?
Oh, yes. Very good question. First, the spin-orbit coupling does not affect the location of the topological quantum phase transition point. Okay, so a lot of people are confused by that. Spin-orbit coupling, you notice the condition for the topological phase transition is that your Zeeman splitting should be equal to square root of chemical potential square plus gap square. Spin-orbit coupling doesn't come in anywhere. But spin-orbit coupling is extremely important. If you didn't have spin-orbit coupling, on the topological side, the gap will always be zero, because the gap on the topological side is proportional to the spin-orbit coupling, which means that you want very large spin-orbit coupling. Because if your gap is very small, you have to work at temperature much smaller than the gap, right? So if your gap is, right now, that's a very big problem. Right now, our calculated gap is like 50 microvolt, which basically means that they have to work, below 50 millikelvin, which is not very good to create technology, right? So what would be very desirable, and I'm not the person to do that, to think of materials which are like indium arsenide and indium antimonide, but have much stronger spin-orbit coupling. This is a material science problem. That would really, really help, because imagine if you can make the gap 10 Kelvin, because spin-orbit coupling is very large, you work above liquid helium temperature. Many of these problems you can solve more easily. So spin-orbit coupling determines the topological gap, size of the topological gap. In fact, it's directly proportional to spin-orbit coupling. So it's a very, very important parameter.
Thank you, Lucas. Thank you. And there's a question now from Fabio Ribeiro. Fabio, you can ask your question.
And thank you, Rodrigo, for the opportunity. Professor Sankar, thank you for this awesome talk. Let me make some questions and one comment from you about the topological transition. How do you guarantee that it is not of Lifshitz type? Because in one slide, how do you guarantee that this topological transition is not of a Lifshitz type?
That it's not a pi shift, you mean?
Lifshitz type.
The thing is, I'm not sure what you're asking. Experimentally, I just told you there is no transition at all. Experimentally, it's just disorder-induced zero bias peak. There is no transition at all. The thing that looks like gap is not a gap. Those are just two undraped bound states coming down. So let's just go to a picture so that what we are talking about becomes very clear. Okay, I can do it. No, maybe yeah. So here, this is experiment. This thing that's coming down is undraped bound state, and this is another undraped bound state. There is no transition here at all experimentally. Okay. Theoretically, of course, when you're looking at the good Majorana, so let me go to a good Majorana picture because I want to answer your question in precision. I like precision. Okay. Here, good Majorana. This is a lot of disorder, but doesn't matter. This is indeed a gap closing, and there is a topological quantum phase transition. Theoretically, we know it's a topological quantum phase transition because we control everything. Theoretically, we are doing the calculation. So experimentally, topological quantum phase transition has not been seen, I believe, because they have not seen this gap opening. Remember, I said right in the beginning that what is the key feature of topological quantum phase transition? In fact, there are two key features. Experimentalists totally focus on the feature that beyond the topological quantum phase transition, you will have these Majorana zero modes, these non-abelian modes at two ends. Okay, you will not have it to the left. But there is another key feature: a gap must close and a new gap must open, because that's the only way a trivial system can become topological. Most theorists, if you talk to them, believe this gap closing and gap reopening is a much more important feature of topological quantum phase transition. Experimentalists, there is no signature at all in any experiment of a gap reopening, and they have to see that somehow. And in fact, in my conclusion, I hope I have that statement. If I don't, then I erred. Bulk gap opening. Okay, this is the bulk boundary correspondence that you hear about in topology. The boundary is the topological, the Majorana. The moment you have something in the boundary, bulk gap must close. So if you just see what you think to be Majorana, but you did not say bulk gap closing, you did not have a phase transition. So that's the long answer to your question. So theoretically, there is no issue of lift shifts or anything because you know what is going on. Experimentally, they have not seen the transition, I believe.
Right, thank you. Another is about one comment of you, because as you might know, the Sergey and the guys from Delft create a table with 5 criteria to establish if you see a Majorana mode, a Majorana zero bias peak.
I really don't want to discuss those things because they are like, I mean, I'm talking about like graduate level physics. That's like pre-elementary school kind of statement. I do not think in a serious conversation, you should bring that up, okay? He's saying nonsensical, trivial things in his own way and tweeting them, and people who do not know the subject are jumping up and down. I mean, I don't want to discuss that. I don't want to dignify that by discussion. I mean, I think everything there is already here, okay?
Okay.
I mean, if it is not, then please point me to that and I can respond to that. If there is something there that I did not cover, please bring it up. But I do not want to dignify that by having a long discussion on it. Okay, I hope you understand what I'm saying, okay?
All right, thank you for your answer.
There's another question from Belita.
I said I had 2 comments.
Yes.
Now, first, I apologize for not acknowledging that your seminar was, as always, very exciting, very stimulating, and motivating. I have a
very
question.
Loud.
Huh?
And very loud also.
So I have a sociology question about physics research. And I noted, looking at your publications, that you've been in University of Maryland since 1980. So that's about 40 years.
Mm-hmm.
And your most cited papers are done in the last 5 to 7 years. And you have focused for 80 years.
Yeah.
Is there a trend, or you think you're doing more important work now?
Yeah, I'll tell you. In fact, I, of course, have thought about it. It's not like I became smarter or I started working on 3 things happen to make this happen, okay? Item number 1, in physics, always the most recent papers are cited the most, okay? This is, you can go back and it's always true, always, okay? Most recent papers always are cited the most. So that's explains. No, I will answer all part. I know what you're going to say. But the definition of most always goes up. I don't know whether it's because more people are coming into physics or people are citing more, what, okay? But the last one is the most important thing. Some of the things I have done more recently, people are not citing me even when they should not. You see, you get a lot of citations and people cite you even when they should not, okay? That started happening last 10, 15 years, maybe because I'm an older person, so people don't feel comfortable. People think, oh, it's safe to cite him, okay? So, but the citation psychology is very, very like strange. It's very hard to explain. So I cannot explain it, except to say that probably in last 20 years, what I have been doing is very, very topical. Before that, I worked on quantum Hall effect, which is not a big subject. If you don't work in a big subject, you're not going to get a lot of citations, okay? So that's a sociology, What are the most cited papers in physics, Belita? Do you know? The most cited 100 papers in physics?
Weinberg, I don't know.
No. Who knows? All 100 most cited papers in physics are band structure papers. Every single one of them. Every single one.
Anderson localization?
I'm telling you the truth. Top 100 most cited papers in physics are all band structure papers. Okay, the only 2 that I'll call non-band structures are Hohenberg and Kohn and Sham. But those are band structure also. Every other one is creating this functional, creating that functional, creating this code, creating that code. I'm not going to name the individuals. And why? That's because those papers are used by chemists, so citation is a very tricky business, okay?
So you think your physics is always as good as before?
If you're doing physics to just do good physics, you'll never do good physics. Never. Anybody who sits around saying, I'm going to do good physics, is never going to do good physics. You should work on problems you're interested in. I'm only interested in answering questions I have. Okay, I could not care less about what others think. Only reason I publish is because students and postdocs need papers, So I think what has happened is that some of the things I have been doing more recently, graphene, spintronics, and this topological thing somehow has become very active areas. And things I did before, which is more basic many-body theory, quantum Hall, and so on, were more fundamental areas, okay? So if you want to distinguish, perhaps, that's the distinction.
Okay.
So let me take a question from YouTube. There's a question from Greg Mazur. Would semiconductors with high dielectric constant could help screen charge impurities and thus reduce charge disorder?
Yeah, this is a very good idea. In fact, we even proposed in one of the papers that maybe they should put some material which has very high dielectric constant in between as a layer. But the problem is that just having high dielectric constant is not enough. These material dielectric constant of the order of 10, not very small. You also need large spin orbit coupling and large G factor, something I did not emphasize, but it was in one of my slides. Why do you need large G factor? Because you don't want to be working at 10 Tesla magnetic field, right? Because what you want is large Zeeman splitting. You can have large Zeeman splitting with a small magnetic field if you have large G factor. And trust me, we went through a list of materials, in 2009-10 when you were writing these papers, and we could not find anything other than indium arsenide and indium antimonide that satisfies all the criteria. But that doesn't mean it doesn't exist. It's not my strength. Okay, this is really a band structure material science question, and I have a feeling that the eventual material where, if this thing pans out and technology, it becomes a technological subject, eventual material would not be indium arsenide and indium antimonide, just as our transistors are not made of germanium and our three-terminal devices are not made of vacuum tubes, okay? But what that would be, of course, I do not know. And if I did know, I probably will take a patent and write a paper. But it's important to think of new materials. Your question is right on the money. It's very important to think of new materials, but you have to optimize many things.
Thank you, Greg. And there's a question from Gabriel, which is related to this one. So the question is, are there perspectives to use 2D materials instead of nanowires?
Oh, our original proposal was 2D. This 1D is just taking the 2D and making it 1D. All the physics I described is already in 2D, okay? Yeah, there are even some papers, but in 2D, the problem is that your Majorana is not localized, right? Majorana is running around the edge of the 2D. Remember, Majorana is a boundary mode. In 1D, the boundary is already localized, right? Because it's a point. But in 2D, it's going around the 2D boundary, so you have to apply a magnetic field to create vortices to localize it. And there is a lot of work. I have done some work on it also, on this iron-based superconductor, where it's a 2D material, iron-based superconductor. People have seen zero-bias peaks in the vortex cores through STM experiment. And it's a very active area. And a lot of people believe that they are Majorana modes. And I think it's a very exciting research area. And I think people should work on it because we are physicists. But I just don't see how you're going to make topological quantum computer out of it. How are you going to move those vortices? See, semiconductor, the great thing is that you don't really need to move the end Majorana, right? Majoranas can stay there. You just use the gate and empty the semiconductor. Majoranas go away. And then, gate somewhere else. It will look like the end mode moved. The great thing about semiconductor is you can gate. If you have like a iron-based superconductor and you have these vortices, and let's accept, for argument's sake, those are Majorana modes, that's great for fundamental physics, but it would not help create a topological quantum computer. But I think it's a very exciting area, and I strongly urge people to work on it.
All right. So, so I don't see any other questions. So as we usually do, I will invite everyone to open their microphones and give a hand of applause to Professor Sankar Sarma for this very nice talk.
Thank you all for your attention. Okay.
Thank you again for accepting our invitation.
No, this was fun. A lot of good questions, and I hope I made sense at some level that I was cautious, but not pessimistically so.
It was right there. Yeah, it was very nice. So I will end transmission now, and the YouTube transmission.
Okay, thank you. Bye-bye.
All right. Thank you, Sankar. Thank you very much.
Bye-bye. Belita, bye-bye.